Okay, so this is an update. I posted a few days ago saying that I had figured out biomarkers of aging, and I've made tremendous progress, but there is a lot of information out there. So I haven't converted all of the NHANES data yet, but this is enough to show you really cool stuff and also to show the fundamental concept of it. So here's the current system, the current array of data. And we're going to go through each of these. These are all scatter plots of various biomarkers as they, according to age, and they're all standardized on the same scale. So we're going to go through no change first and just work our way through each of these categories. So what things don't seem to change with age? According to NHANES and their large body of information, body fat percentage doesn't seem to have much of a change with age. Albumin creatine ratio, it just seems to kind of be sort of steady across. This is the zoomed out version. I removed outliers in order to get a more clear picture. Anyway, alpha carotene doesn't seem to change with age. There doesn't seem like there's much of a trend. Basophil percent. Basophils are a type of cell. That percentage doesn't seem to have any impact from age. Blood chromium, blood cobalt. I wouldn't expect these things to change. It's a couple of heavy metals. Your exposure is probably due to specific circumstances. C-reactive protein was surprising. So I've always assumed that C-reactive protein was something that was very involved with aging because everyone seems to care about it so much. But NHANES suggests that apart from a few outliers, if you take these 4 outliers out of the equation, it really doesn't seem to change at all. There's some scattered, high levels of CRP, but overall, there's no trend. DEXA, total percent fat as measured by a DEXA scan, doesn't seem to change with age. Gamma tocopherol doesn't seem to change with age. HDL cholesterol, very weird. So it doesn't like it's always a thing, right? It's always a thing. This HDL cholesterol and C-reactive protein, I'm sure are very vital signs to understand for acute risks for heart and other types of diseases that you could get. But the trend, at least as measured by NHANES data, doesn't seem to show a change with age, and that's really weird. High density lipoprotein. So HDL. This one's from 2017. HDL 2017. Where is it? HDL cholesterol. Oh yeah, I renamed the files, but I didn't update the actual image itself. So this is HDL from 2017. This is from 1999. I want to make sure you know that the data seemed consistent. And we'll go through more of that kind of stuff later, but it doesn't seem to have any correlation to age, which is really weird. Klotho, it doesn't appear to be correlated to age, at least as much as far as this body of information is concerned. So we've got soluble Klotho, and this is also soluble Klotho. This is from 2015 to 2013's data. And if we look over here at the Klotho, we can see maybe a potential wedge formation, possible. So I was on the fence about this one, but if you look at it, it doesn't seem like there's a really obvious shift. So the next step for all of this is to do statistical analysis to get median line, not the average. Averages are terrible. Get the median values for all of these and see if it kind of follows this wedge formation or if this is just an artifact of how the data is being displayed. But it's just at first glance, it doesn't seem to have any correlation with age. I'm harping on this because everyone knows that Klotho is this longevity gene / longevity protein. And so it's been like over and over just hammered into everybody like, oh, this is clearly a longevity thing. And it's like, well, then how come these 80-year-olds are having the same levels of Klotho as these 40-year-olds? This doesn't make any sense. So if it is a longevity protein. So anyway, here's the unzoomed version from 2015. It just seems, like, yeah. Okay, moving on. Liver median stiffness doesn't seem to change with age. Monocyte number doesn't seem to change with age. Anything that's unlabeled in terms of years is all from 2017. Monocyte percent doesn't seem to change with age. There might be a slight, I don't know. It's hard to tell if there's any kind of shift here. You can see that the 5 is like visible at the tail end. So maybe it goes up or something. I don't know, but it doesn't, there's not a really clear trend line. Like you'll see later what I'm talking about. Neutrophil number doesn't change with age. Nucleated red blood cells does not change with age. Red blood cell count. This is probably misappropriated. Let's take a look. Red blood cell count. I would say maybe this belongs in development. So I'm gonna put it in there, and then we'll get to that later. Okay. So red blood cell, nucleated red blood cells, red cell width doesn't seem to change with age. Retinol palmitate doesn't seem to change with age. Retinol stearate doesn't seem to change with age. Serum insulin does not seem to change with age. Kind of weird, because diabetes and all that kind of stuff. I'm assuming that this, I don't know. We'll get to it later. These are all tentative, and I'll explain that as well later. So serum insulin doesn't seem to change. Yeah, that's the zoomed out version, zoomed in version. Serum iron doesn't seem to change with age. Toluene arsenic, transferrin receptor, triglycerides, surprisingly. This is from 1999, 2017, zoomed in version. Can't really see much of a trend here. Urine albumin, urine flow rate. This is all stuff measured by NHANES, and so I'm putting it in here. Urine iodine, urine perchlorate, no change with age. And I think that's the end of the things so far that I've found that don't appear to have any trend. Again, so what this is a conversation. This is a conversation that's actually driven by data. I'm showing you what the data looks like and why I think what I think. And you can come back and show a different set of data, or you can show a different interpretation of this data, and I will change my mind if I can see what your data is and how you came to the conclusion, if it makes sense. Some of these things will probably change over time, but this is my initial array of, I guess, categorization for all these things. So let's just move on. Loss of control. This is going to be all the things that appear. The loss of control is defined as like the base stays the same, but like there's a big like wedge form of outliers and data that just sort of starts to spiral. Like your body is like losing control of some aspect. And so this is different from accumulation. I need to go into this right now. So this is different from accumulation, where accumulation is like there's actually a change in both the top and the bottom, where it's like accumulating over time, whereas loss of control is just you're creating a spread of data. So let's just go into it. So 20-foot walk time seems to have, there's a loss of control. Cystatin, see how these people at 85, some of them have the same biomarker data as a 10-year or a 20-year-old or a 15-year-old, right? But some of them have these really high values, but you don't see those high values during youth. So the high values only appear to come out later in life. Alpha tocopherol seems to have exhibit loss of control over time. Blood ferritin appears to have, glycohemoglobin A1C. So you can see that the lower bound, these 80-year-olds, some of them have the same levels as a 20-year-old. But it's kind of absurd to think that this 80-year-old is as healthy as a 20-year-old, just in general. So really, this loss of this, I guess, greater variance is what I'm talking about here. Yeah, so anyway, blood mercury seems to be destabilized with age. Cis beta carotene seems to come up kind of. There's a bunch of outliers here, so I'm not completely sure about this. This might actually just be like no change, but I put it in here for now. Again, these are tentative. Lutein and zeaxanthin. So it seems to have some sort of wedge shape with a solid base. Plasma fasting glucose seems to get highly destabilized as you age. Red blood cell folate, same thing. Serum vitamin D2 plus D3 seems to destabilize, mostly due to D2. D3 seems a bit more stable. D2 clearly has this wedge shape going on. As people age, there's this more and more outliers for vitamin D2 levels. Sex hormone binding globulin, kind of a bit. It's really weak. This one's kind of weak. Again, these are from two different years, 2001, 1999. It's kind of weak. Confidence is not there for that one. Okay, development. Development category is characterized by trends which have one trend up to around age of 20, and then they flatline afterwards. So the change is only up during the development period. Now, some people believe that development is not part of aging. I disagree, but I do think that trends like this should be kept separate from other types of trends, because you need to know there's definitely some kind of inflection point that occurs around the age of 20, and we would like to know what things just sort of flatline after that level and what things don't flatline after that level. So cell membrane capacitance, characteristic frequency, these are bioelectric resistance measurements that NHANES did early in like 1999. I'm not sure if they're still doing them. Extracellular fluid resistance, intracellular fluid resistance, total body water volume, VO2 max. Surprising that this one kind of has this different sort of a bulge here. I'm sure if they had kept it down, it would have. I'd like to see this data. I would like to see what happens back here. I'd also like to see what happens way out here, but they didn't capture that. So as far as we can tell, it just flatlines after the age of 20. Kind of weird. Especially since a lot of people seem to put a lot of stock into this. So alpha cryptoxanthin, very slight. It's almost not a lot of confidence in this one in terms of the categorization, but it does appear to have a different motif prior to 20 than after 20. Beta cryptoxanthin, same thing, kind of weak on the interpretation. Blood pressure, 60-second pulse, seems pretty stable after 20. Blood selenium levels, same thing. Body mass index makes a lot of sense here. The DEXA total area, DEXA bone mineral content, DEXA bone mineral density. I'm very interested in what happens to bone mineral density after the age of 60. It's osteoporosis. I'm not sure when it hits a lot of people, but we can see that maybe it's starting to come down, and then the data just ends. I just wish that they got more data. But as far as this is concerned, it doesn't appear to change with age. At least it doesn't change like consistently. It'd be very interesting to see if there's an inflection point over here and it just starts to drop off. But yeah, this is associated with osteoporosis, so it's kind of important, and it's weird that it doesn't change with age. Total fat content doesn't seem to change with age after the age of about 30. Eosinophils. I don't know how to pronounce this. This is a type of cell. So this is again really weak interpretation. It might just be a non-changing value. So percent, a little bit stronger, but still it's, you know, it's kind of weak. Estradiol seems to be very clear. One motif here, and then goes across again. A motif here comes across. Height, very obvious. This is like the clearest, of these things. Interestingly enough, if you look at height from a zoomed out perspective, you can see that it kind of drops a little bit over time. And you can see that here. So you see the 190 and how there's like progressively more white spaces as we get to the right side. Kind of interesting. Hematocrit. So we've got one motif, yeah, again, hemoglobin, lymphocyte number, lymphocyte percent, mean platelet volume appears to be this motif, barely. Neutrophil percent, very clear. Platelet count, it's kind of clear. Red blood cell count, very, very weak. This is the one I just recategorized. It's like I might just get to the next year's data and then decide, oh no, never mind. But for now, this is where it's going. Vitamin C, I only put it here because of this small wedge on the bottom right here. It might be reclassified later. Here's the zoomed out version. This outlier causes the entire thing to get shrunk down. So it's like, it looks like no change. But if you zoom in on it, maybe there's a situation with where during development it changes. Total cholesterol, yeah, it does seem like there's a shift around the age of 20, but again, the confidence is not there. Upper leg length, very clear. Urine nitrate, not as clear, but still seems kind of clear. Urine perchlorate, similar thing going on. Weight, very clear. White blood cell count, pretty clear. No change after development, but a sort of a reduction from age of 0 to, I don't know, around like 15 years old. And that's about, okay, that wraps it up for the development category. We're gonna skip the demographics, striation, and the cannot classify. I'll leave those to last. We have something called arc of life, and I used to have a lot more in here, but then I kind of reclassified some of them. There's right now it's just basically diastolic blood pressure and vitamin epi D3. But the idea is that some biomarkers seem to rise and then fall back down with age. So over the course of the lifespan, this is 2015 diastolic blood pressure. This is 2017 diastolic blood pressure. It just kind of follows this arc, which is weird because systolic blood pressure doesn't follow this arc. These values down here are like artifacts of how NHANES records data, so you can ignore that. Yeah, so that's interesting. Epi D3 is like an inverse, but you know what? I might like find other years of data and just decide, oh, this is just a weird, one-off. So anyway, adult consequences are kind of interesting. It's a sort of not really age-related, but kind of. Blood cadmium, heavy metals accumulation typically doesn't happen when you're a child. And then it kind of just changes. It's not quite an inverse of development. It's more like once you become a certain age, you'll get exposed to certain, aspects of the world, like working or, doing other things. And then your biomarkers will shift. It is a age-related phenomenon. It's not necessarily biologically aging, but it's nice to keep track of this kind of stuff, especially since NHANES has all this data anyway. So blood ethylene dioxide seems to have like very compact low values here, and then they're scattered all throughout adulthood. It doesn't seem to be much of a trend. Blood lead, again, doesn't seem to, so cotinine and hydroxycotinine are both products of smoking. You can see how at an age where a lot of children will transition to start the age of smoking, they'll start to accumulate it, and then it just kind of like, it's just all over the place at that point. Same thing here, slight trend, but again, this is a product of smoking, not a product of aging necessarily, although, it's nice. Again, it's nice to know. So finally, we have accumulation and loss, and this is kind of the more classical motifs of aging, which is, let's do one that's really obvious first. Telomere, you can see that there's a shift downwards of both the top and the bottom ranges, and it's over the course of life. This seems to be fairly consistent. So let's go back to the start again. Jackknife balance. This is the ability to balance. You can see that it decreases. I put rep 1 and rep 30. I thought maybe there's a change. No, not much of a change. It's all 1999 data, and it seems to decline with age. I do wonder what it looks like in this bottom section that has no data, but it is what it is. Blood manganese, very, very low, like it's almost imperceptible. So, but it does seem like it does decline. So it might not change or it might decline. I just put it in here, low amount of confidence on this one. Maximum inflation level, this is for blood pressure. Maximum inflation level in millimeters of mercury. It seems to have this is for 2017, this is for 2015. It does seem to have this accumulation where you don't see any like 60 to 80-year-olds with a value in this range right here. And then you see them having higher top end. Mean cell hemoglobin, it looks like development, but then it also kind of keeps going up. So it's a kind of a hybrid of both. There's one slope for up until like age of like 22, 23, something like that. And then it kind of it doesn't flatline. It keeps going up, but at a different rate. So kind of interesting. Mean cell volume. Again, same situation, 2 different slopes. There's some kind of inflection point around the end of development, but it does continue to go up. Mean telomere ratio goes down, or yeah, telomere length. Telomere, it's not telomere length. This is the TS ratio. I forget exactly what that means, but it's correlated to length. It's going down. Michael Fossil has problems with the idea of measuring mean telomere length, and I think he's correct. I think that there's better ways of measuring telomere length, but I'd like to see the scatter plots of that data if they can provide it. All right, peak force, newtons, clearly declining. This is for muscle strength. I'm not sure which muscle. In NHANES data, they'll describe which muscle they actually measured. Retinol seems to, I'm not sure why it's going up. I'd have to reread that section of the report and find out. Systolic blood pressure goes up and also becomes destabilized. So it's both an accumulation and a loss of control, it looks like, where there's greater variance as well as just greater values in later life. Again, here we go, another systolic blood pressure. Total iron binding capacity, kind of weak. I'm not sure about this one, but it does seem like here versus here, it kind of has this sort of trend. Translycopene, I'm not sure. It kind of maybe, not confident about this one. Unsaturated iron binding capacity, slightly maybe. Anyway, so a couple of them are a little iffy, but overall, I think that there's a lot of these. So anyway, those are the categories that I came up with. It's weird that, not weird, but it's interesting that they only, like, all these biomarkers really fit into just a few different motifs of how they behave. Like, they're not all over the place in terms of their patterning. It just kind of falls in a couple different categories. We'll go into cannot classify first, and this is a good one. Okay, so for instance, basophils number, there's just not enough data, and there's not enough resolution on the data to get any kind of trend. LDL cholesterol, hard to say. I was like, oh, maybe it's development, but then I don't know. It's all over the place. This is so these are the cholesterol levels from 2017 measured in 3 different ways. And I thought this was like arc of life motif. And then I saw 1999's data and I'm like, well, this doesn't show arc of life. This shows just a gradual, it's not even accumulation because it's kind of like flatlining, but not really. It's just a weird shape. So I'm holding off on classifying this for now. Liver median, a controlled attenuated parameter. I'm not exactly sure what this measures, but it doesn't have enough like resolution. Like the scales need to go way higher. But this is actually what the NHANES data, like this is the totality of the NHANES data. I didn't cut down on the scale. It's literally like a big, there's like this weird box drawn around it. So clearly not enough resolution on this one. Hearing there's a clear shift, but they don't capture this whole center section. So what this is measuring is the decibel volume level necessary for a person of a certain age to hear at 4,000 hertz frequency. As that decibel volume goes up, it means that your hearing is getting worse. It means that you need a higher volume to hear the same sound. So a younger person can hear these sounds much lower volumes. Higher person or older person needs to have higher, and that's across for 6,000 or 6 kilohertz and 8 kilohertz, and seems to be across the board for a whole lot of other ones. There's just they did the entire range, but I just like it's a lot of data, and this is enough to know that this isn't going to be a good this isn't a good pool of data to draw good conclusions from because it's missing this whole center section. Okay, testosterone. This is one of the more interesting things. Okay, so here we have 1999 and 2001. And these ones, like, look, okay, check this out. Clearly declines with age, right? This just seems like very obvious. Kind of obvious. Declines with age. Yeah, of course, it declines with age. Comes up with development, declines with age. And then in 2013, it's like, wait, what? It doesn't, the pattern's starting to disappear, maybe, I don't know, kind of. And then 2015, it's like, wait, what? What happened to this clear decline with age pattern? And it turns out in 2013, they switched their measurement methods of how they measure testosterone. And they also measured it in both genders, which is why this is, I pulled out all the male data for 2013 and 15, but I didn't have to do that because in 1999 and 2001, they only measured males. So these are all male-only data, all 4 of these. But in 2015 and 13, they also measured women. So this is interesting because in 2014, there's this piece of data. This is not NHANES data. This came from a paper. This paper, a validated age-related normative model for male total testosterone, shows increasing variance, but no decline after age of 40 years. This paper came out in 2014, and it shows that while there's a subpopulation of people who lose testosterone, it seems like most people are just straight across the board. So like this has been known for a really long time. Like, of course, testosterone declines with age. And then there might be a shift in like just like it might have been an artifact in how they measured it or something like that, and maybe it doesn't. But this is really important. Like, sorry, this is really important because this is like central to the thesis of the whole germline control thing. If we need to know one way or the other what's going on here. Now, not all updates, not all progress is forward, and sometimes updates break things. So what if this is like the right one, but I suspect that it doesn't decline with age. But anyway, it warrants further investigation, and it's really useful to understand, like, just to see the data, like the raw data, and be like, oh, here's what it looks like. So that was really important. So let's go back out to That was a cannot classify section. This is the demographics striation section. So if we look here, so we're gonna get into demographics information now. So if we look at, for instance, systolic blood pressure for males, white, Asian, other ethnicity with low income or lower than the high income people, we see this distribution that looks very similar to the what's it called? Accumulation systolic blood pressure. There we go. So here's systolic blood. Oh, that's 2015. Let's compare directly 2017. Okay, here's systolic blood pressure for the entire population, and here's for this sort of demographically sliced up section of the population. Very similar, right? Kind of, you know, the spread is not as much here, but a very similar trend. But if we look at high income individuals, suddenly this accumulation pattern disappears. And what you get is a sort of a rise and then it sort of flatlines through age. So if you want to interpret this one way of interpreting this is being rich prevents you from losing control over your systolic blood pressure, which if you think about the nature of obesity and overweightness and how that is tied into blood pressure, like it makes a lot of sense, but it means like, you know, income is an aging intervention, right? And that's, you know, this is the kind of information that comes out of looking at demographics. And Haynes has got a bunch of demographic information. A lot of it seems kind of useless, but some of them are very crucial. Gender, income level, ethnicity are among the more important ones. And we can do this kind of stuff for every single piece of information. Obviously, it's a lot of work, and I'm kind of hoping that somebody else has already done this, and maybe I'm reinventing the wheel, but I haven't seen anybody else's wheel, so it's really annoying, and so I had to do this on my own. Anyway, I digress. A1C. So here's A1C for all males. Here's A1C. Oh, let's close this over here. Here's A1C for Asian, white, other ethnicity males. And then here's A1C for low wealth and high wealth. Again, not much difference. Some difference maybe, but not a lot of difference. Not like what we saw with systolic blood pressure, right? So sometimes the subpopulations will match the greater populations, and sometimes they'll be very different. And that's, I think that's very useful and important information to have. So that's pretty much it. Caveats, let's see here. So longitudinal data shows an individual's lifespan. Cross-sectional data, like NHANES data, also takes into account the past. So it's not showing like one person's trajectory over time. It's also showing like if you have shifts of legality of stuff, like let's say that people banned smoking in the last 30 or 40 years in many places, right? Which is a thing that kind of happened. You'll see a shift that's age-related, even though it's not actually age-related, because it looks like everyone who's older than X has some condition attached to them. But that's more due to historical events rather than their individual pathways. So cross-sectional data has that. But otherwise, yeah, there's a lot here, and I'm going to continue doing more. Just have to get off my lazy ass and then sit back down on my lazy ass because this is all computer work. So anyway, thanks for watching till the end. I'll see you later.